V patterns, fire burns up in a V-shaped pattern, so a fire that starts at an outlet against a wall leaves a charred pattern that points to the origin. A very narrow V-shape might indicate a fire that was hotter than normal, such as one helped along by accelerant. Spalling is the cracking and breaking off of concrete or masonry due to high temperatures and thermal stresses. Large blister charring or alligatoring indicates that the fire evolved rapidly and produced high temperatures, signs that a liquid accelerant may have been used, and an irregularly shaped or serpentine burn patterns often results from a flammable liquid being poured on floor surfaces. Forced entry is the illegal entry into a building or property by using force, such as breaking a window, forcing a door open, or picking a lock. It is often associated with burglary, theft, or other criminal activity. A tampered safety system is a security system that has been intentionally altered or modified to bypass its intended safety features. This can be done for various reasons, such as to disable alarms, prevent monitoring, or conceal illegal activities.
Good day, sir. I will discuss the physical evidence analysis and chemical analysis. So let's begin. Physical evidence analysis in arson investigation is vital for understanding the cause and origin of fires. Investigators focus on several indicators, including accelerants, multiple ignition points, and unusual residues. Accelerant indicators. Accelerants are flammable substances used to enhance or spread fire. Common indicators include presence of ignitable liquids. Investigators analyze fire debris for residues of substance like gasoline or kerosene using techniques such as gas chromatography and mass spectrometry. The identification of this substance can indicate intentional fire setting. Pour patterns. Unusual burn patterns such as V-shaped patterns or trails lead to the fire's origin, can suggest the application of accelerants. Multiple ignition points. The identification of multiple ignition points is a significant clue in arson investigations. Distinct burn areas. Fires that start in several locations simultaneously may indicate deliberate actions. Investigators look for signs like separate burn patterns and the presence of accelerants at each point. Analysis of burn patterns. Understanding how the fire spread from these points can help establish whether it was intentionally set. Trails or unusual residue. Investigators also examine trails and residues for additional evidence, such as unusual residues. The presence of chemical residue not typically found in household materials can indicate the use of accelerants. These residues may be analyzed to determine their composition and source. Physical clues. Other physical evidence such as charred debris and specific burn marks can provide context about how the fire was started and its intensity. So, let's proceed to chemical analysis. So, what is gas chromatography, mass spectrometry, or GCMS? So GCMS is a powerful analytical technique used to identify and quantify different components in a sample. It combines two techniques, gas chromatography and mass spectrometry. What is gas chromatography? Gas chromatography separates components of a sample based on their boiling points and interactions with a stationary phase. The sample is vaporized and passed through a column containing a stationary phase. Different components travel through the column at different rates, leading to their separation. Mass spectrometry identifies and quantifies the separated components by measuring their mass to charge ratio. The separate components are ionized fragments and then detected based on their mass to charge ratio. This information is used to identify the components and determine their relative abundance. So, in summary, GC or gas chromatography separates the components of a sample, while MS or mass spectrometry identifies and quantifies the separated components. So GCMS is used in a wide range of applications, including environmental analysis. It detects pollutants in air, water, and soil. Food analysis, identifying food additives, contaminants, and authenticity. It also used to drug analysis, identifying and quantifying drugs and biological examples. Forensic science, analyzing evidence from crime scene. Lastly, medical research, studying the composition of biological samples. So, what is headspace analysis in GCMS? It is a technique used to analyze volatile compounds in a sample without directly injecting the sample into the GCMS system. Here's how it works. First, sample preparation. The sample is placed in a sealed vial, often with a small amount of headspace or empty space above it. Second, heating. The vial is heated to a specific temperature, causing volatile compounds to vaporize and equilibrate in the headspace. Third, sampling. A small portion of the headspace gas is injected into the GCMS system. And lastly, the separation and detection. The GC separates the volatile compounds based on their boiling points, while the MS identifies the quantifies each compound based on its mass to charge ratio. There are two types of headspace analysis. First is the static headspace. The sample is heated in sealed vial, and the headspace gas is sampled directly. Second is the dynamic headspace. The sample is heated and purged with an inert gas, which carries the volatile to a sorbent trap. The trapped volatile are then desorbed and injected into the GCMS. Headspace analysis is a powerful tool for analyzing volatile compounds in a variety of samples. It offers several advantages over direct injection methods, making it a valuable technique in many fields. That's all, thank you.
Chemical analysis, fire accelerant residue analysis or FARA. This specialized analysis focuses on identifying and quantifying the presence of accelerants in fire debris. FARA can help determine the type of accelerant used and its concentration, providing crucial information for investigators. Ang FARA is a process used to find out if a fire was started on purpose using flammable substances like gasoline, kerosene, or alcohol. When a fire happens, investigators collect debris or mga burnt materials from the scene and test it in a lab to check for traces of these substances. So this analysis helps identify what kind of accelerants ang gigamit and how much of it was present. The results are important because they can help fire investigators to figure out if the fire was accidental or intentional. And there is other chemical tests. So additional chemical tests may be conducted to analyze other types of evidence, such as paint, fibers, or soil, which can help to link suspect to the crime scene. Aside from checking for fire accelerants, investigators can also do other chemical tests on things like paint, fibers, cloth or threads, or soil. So these tests help find clues that might connect a suspect to the crime scene. For example, paint analysis can show if a suspect's car or tool left paint traces at the scene. Fiber analysis can check if a piece of clothing matches fibers found at the crime scene. And last is soil. Soil analysis can compare dirt from a suspect's shoes to the ground at the scene. So these tests give more evidence that can help to solve the case.
Good day, sir. So now let's proceed to flame characteristics. Flame color. The color of the flames can indicate the type of material burning. For example, A yellow or orange flame often suggests the presence of carbon, while a green flame may indicate the burning of copper. So now let's proceed to flame height. The flame height of the flames can provide information about the fire's intensity and the presence of the accelerants. A sudden surge in flame height could indicate the use of flammable liquid. Smoke color. The color of the smoke can also be indicative of the type of material burning. Black smoke usually signifies the burning of organic material, while white smoke may indicate the burning of plastics or other synthetic materials. And now, let's proceed to the flame colors and what they indicate. Blue flame, typically seen when burning natural gas, alcohols, or even clean burning materials. Yellow flame, the common color for wood, paper, and organic materials, often caused by incomplete combustion or carbon particles.
Red flame occurs when materials are burning at a lower temperature, often seen with wood or other organic materials that are not fully combusted. Red flames are often associated with temperatures around 600 to 900 degrees Celsius. A red flame can also indicate incomplete combustion. This means there's not enough oxygen to fully burn the material, leading to the releases of cooler, redder light. White flame indicates extremely high temperatures, such as those from magnesium or some metals. A white flame signifies that the burning material is reaching a very high temperature, often exceeding 1000 degrees Celsius to 1800 degrees Fahrenheit. As an object gets hotter, it emits light due to black body radiation. White flames indicate the object is emitting a broad spectrum of light, including all the colors of the rainbow. White flames are often observed when burning fuels that produce high-energy combustion, like natural gas, propane, or acetylene. These fuels have a high heat of combustion. A white flame typically signifies a complete combustion where there's enough oxygen to fully burn the fuel, resulting in the release of a lot of energy and a bright white flame. Green flame can be caused by the presence of chemicals like copper compounds, examples from burning wires or plumbing materials. Copper compounds, when heated, produce a characteristic green flame. This is why copper salts are often used in fireworks to create green colors.
Hi everyone, I am John Philip Amor. Now I will discuss the colors of smoke. First is greenish yellow. The combustible is chlorine gas. Chlorine gas is a toxic, corrosive, greenish yellow gas that is irritating to the eyes and to the respiratory system. Here are some examples how chlorine gas used. It is used as a disinfectant. It is used as an antiseptic. It is used to produce drugs. Gray to brown smoke. The combustibles are wood or paper. Gray or brown smoke occurs when there is a mixture of moisture and hydrocarbons. Bark on woods can stimulate brown smoke as this is the driest and most impure part of the wood. You can also see gray to brown smoke color when there are other stimulants on the wood. Violet. The combustible is iodine. Iodine is found in soil and the ocean. Iodine is mineral found in some foods. Best source of iodine is seafood, eggs, and milk. Iodine vapor causes eye, skin, nose, and throat irritation, coughing, wheezing, and laryngitis. Brown. The combustible is cooking oil. Cooking oil starts to smoke when it is overheated. Cooking oil above its smoke point can release harmful compounds and free radicals, which can increase the risk of inflammation and lung irritation. Brownish to black. The combustible is naphtha and liquor thinner. Naphtha and liquor thinner is commonly used as a solvent, an excellent thinner for oil-based paints, stains, and varnishes. Black to brown. The combustible is turpentine. Turpentine is a yellow-colored, sticky liquid that comes from pine gum or pine wood. Turpentine can cause headaches, dizziness, nausea, confusion, and rapid pulse.
White smoke, often seen when burning organic materials like hay, vegetable compound, and phosphorus. is primarily composed of tiny water droplets and unburned fuel particles. These particles are released during incomplete combustion, where the organic matter doesn't fully burn due to lack of oxygen. Hay, like many plant materials, is rich in cellulose, a complex carbohydrate that breaks down into simpler compounds during burning. Vegetables compound also contain carbohydrates and other compounds, including phosphorus, an essential nutrient for plant growth. Phosphorus is in elemental form, is highly reactive, and can ignite spontaneously in air. When phosphorus is present in organic materials, it can contribute to the production of white smoke during combustion, along with other compounds like carbon dioxide and water vapor. Benzene, a highly flammable liquid, produces white to gray smoke when burned due to incomplete combustion. This occurs when there is insufficient oxygen to fully oxidize the fuel. The white smoke is primarily composed of tiny water droplets and unburned fuel particles, while the gray color indicates the presence of fine carbon particles. As the combustion becomes more incomplete, the smoke turns darker, indicating a higher concentration of unburned carbon. Nitrocellulose, a highly flammable compound, produces yellow to brownish yellow smoke when burned due to the presence of nitrogen oxides released during combustion. These oxides, along with unburned carbon particles, contribute to characteristic color. Sulfur, when burned, also produces a yellow to brownish yellow smoke due to the formation of sulfur dioxide gas, which has a distinct yellowish wood. The intensity of yellow color can vary depending on the amount of sulfur present, the combustion conditions. Nitric acid and hydrochloric acid, when mixed, react violently to produce a yellowish brown gas, primarily nitrogen dioxide. This gas is responsible for the characteristic color. Gunpowder, a mixture of charcoal, sulfur, and potassium nitrate, also generates a yellowish-brown smoke during combustion. The sulfur in gunpowder reacts with oxygen to form sulfur dioxide, which contributes to yellow. Additionally, incomplete combustion of charcoal produces fine carbon particles, which further enhance the brownish-yellow appearance of the smoke.
The brownish to black color of smoke produced when burning certain substances is primarily due to the presence of carbon particles. When substances containing carbon, like wood, paper, or fossil fuels are burned, they undergo a chemical reaction with oxygen. This process is called combustion, the release of energy in the form of heat and light. However, if the combustion is incomplete, the carbon atoms don't fully oxidize. Instead, they form tiny particles of soot. These soot particles are what give the smoke its characteristic brownish to black color. Examples of substances producing brownish to black smoke are wood. Burning wood, especially soft woods like pine, often produces a significant amount of smoke with a brownish hue. This is because wood contains high percentage of carbon. Papers. Similar to woods, papers also contains carbon and produces brownish smoke when burned. And fossil fuels. Coal, oil, and natural gas are rich in carbon and produce a lot of black smoke when burned. Tires. Burning tires, a practice sometimes used for waste disposal, generates thick black smoke due to the high carbon content in rubber. The color of smoke can also be influenced by other factors besides incomplete combustion, such as moisture content, like damp wood tend to produce more smoke and the smoke may be lighter in color, and chemical composition. Some substances like plastics contain chemicals that can contribute to the color of smoke. The color of smoke produced when a substance burns is primarily determined by the presence of carbon particles in the smoke. Black to brown smoke indicates incomplete combustion. Here are some examples of substances that produces black to brown smoke when burned. Wood. Burning wood often produces black smoke due to the high content of volatile organic compounds that don't burn completely. Coal. Coal is a fossil fuel rich in carbon, and its incomplete combustion generates a lot of black smoke. Diesel fuel. Diesel engines are known for producing black smoke, especially when they are not properly tuned or under heavy load. This is because diesel fuels is a complex mixture of hydrocarbons that don't burn completely. And rubber. Burning rubber tires or other rubber products releases black smoke due to the presence of carbon black in the rubber. And also plastics. Many plastics contain carbon-based polymers that release black smoke when burned. It is important to note that the color of smoke can also be influenced by other factors, such as the type of fuel, the temperature of the fire, and the presence of other chemicals. The black smoke produced when substances burn is primarily due to the incomplete combustion, resulting in the formation of carbon particles, which are what we see as black. Incomplete combustion happens when there isn't enough oxygen available for the fuel to burn completely. This can be caused by factors like limited oxygen supply. When a fire is starved of oxygen, it can't burn efficiently, leading to incomplete combustion. Low temperature. Burning at a low temperature can also hinder complete combustion. And fuel type. Some fuels like wood and certain plastics are more prone to incomplete combustion and producing black smoke. It is also important to note that black smoke is not always a sign of incomplete combustion. Some materials like certain types of paint can also produce black smoke when burned. However, in general, black smoke is a strong indicator that the burning process is not efficient and is releasing harmful pollutants into the air. Flame color analysis, while not definitive on its own, provides valuable preliminary information in arson investigations. The color of a flame can offer clues about the type of accelerant used, as different fuels burn with characteristic hues. For instance, a bright yellow flame might suggest the presence of a hydrocarbon base, while a bluish flame could indicate a different substance. However, it's crucial to remember that environmental factors, the stage of the fire, and the presence of multiple accelerants can significantly influence flame color. Therefore, flame color observation should be considered supplementary evidence requiring corroboration through other investigative techniques, such as chemical analysis, fire debris, to reach accurate conclusions about the cause and nature of the fire.